Alright, in this video I am going to explain the concept of the hydride and methyl shift. Okay, suppose you have this reaction which you should be familiar with, okay? This is just a simple addition of a hydrogen halide to an alkene. And this alkene in particular is 3-methyl-1-butene. So if we were to draw the mechanism for this reaction, get a pen here, you would get that, remember that, double bonds are very nucleophilic, they're electron rich, and this is a partially positive hydrogen due to electronegativity. So this double bond, as the nucleophile, will attack this partially positive hydrogen. And as a result of that, the electrons being shared this bond are now posited onto the Cl. Now, according to Markovnikov's rule, Markovnikov's rule says that the hydrogen in the hydrogen halide that's being reacted is going to go to the carbon with the most hydrogens attached to it. Another definition that you might see is that the hydrogen will go to the carbon that is least substituted by alkyl groups. So in this case, which one of these carbons would it be? Would it be this one or this one? It would be this one back here because it has two hydrogens and this one only has one. So we were to write our carbocation intermediate, and this is what this box is for. Here we are going to write our carbocation intermediate. We will write this structure as CH. Take a different color. And that is the H that we added on from the addition of the H of the hydrogen halide. And then this carbon right here is a carbocation. Now, according to Markovnikov's rule, the Cl will then come and attack this carbocation. But there's something interesting that happens in this intermediate form, and it's kind of like a form of resonance. So if you remember resonance, you remember that structures usually move electrons around, the bonds move around to become a more stable species, okay? And that's really the point of this hydride shift, okay? I want you to look at this carbon right here. If I was to add that chlorine from the reaction onto this carbon, this carbocation that this chlorine would be added on would be what type of carbocation? Would it be a primary carbocation, a secondary carbocation, or a tertiary carbocation? Well, the answer is secondary because it's connected to two other carbons, right? So we know from our hierarchy of order, when it comes, I'll go down here, when it comes to carbocations, and I'll write it like that, we know that tertiary is greater than secondary, which is greater than primary, right? So if we could somehow shift this hydrogen that's painted in blue here over to this carbon, then this would become our carbocation. Now, why do we want this to become our carbocation? If this carbon was our carbocation, how many carbons would be attached to? It would be attached to 1, 2, 3, and then that would be a tertiary carbocation. And that tertiary carbocation is a lot more stable for this Cl to come and attack. And that product would be a lot more favored than if it was in this middle carbon. So we'll write a resonance form, and an equilibrium exists here. And I like to just do this. I like to draw an arrow going this way. Like that. And then I like to draw a smaller arrow going this way. And it really explains what's going on. Okay? So this side, what I'm about to draw, is a lot more favored than this carbocation. So I'm going to write at the top of this H minus, which is a hydride, right? And I write shift. Okay? So it shows what's going on in this intermediate form. So what happens here, we'll draw our electron arrows, is that this electron, this bond right here with the hydrogen and the carbon, these electrons are going to come and attack this carbocation here. And that entire hydrogen with those electrons, the hydride ion, right, a negatively charged hydrogen, will come and attack this carbocation. Okay? And that leads to a resonance form of, and I'll draw it, this space that I have here. So this guy shifted this way, as you can see there, and this was the original hydrogen added onto the alkene. So far all we've done is that this double bond broke via this reaction. Okay, we're trying to keep it simple here. This nucleophilic electron-rich double bond came and attacked this electrophilic hydrogen in HCl, and as a result, this Cl minus became a counter ion, and those electrons in that bond were deposited onto it. So before the Cl is added, we know that the H will go to the carbon with the most H's attached to it, according to Markovnikov's rule. And there you have it, leading this as a carbocation. But this carbocation isn't the most stable of carbocations possible. And because of that, we have the hydride shift. It's kind of like the molecule's internal way of saying, hey, you know, we need stability here, and we're going to take charge. So what happens is that this hydrogen, including those electrons, will come and attack a positive carbocation. And that's really the shift. He comes over with its electrons and onto this carbon, making way for a carbocation. It's on the carbon that it used to be on. Okay? Now this carbocation is a tertiary carbocation. It has 1, 2, 3 carbons attached to it. Now the Cl counterion that we had at the top is in a better place to attack. And its attack will occur onto there. Okay? So our desired product at the end will look like this. Cl. This is our hydrogen. And then this was the hydride that shifted. So as you know from this reaction, when you add a hydrogen halide in the form of HX this X being Cl, to a alkene, you will get something called a haloalkyne, right? Here's the haloalkene. Here is the halogen, and this is an alkene, the single bond structure. But the important thing to take from the hydride part is the shift and why it occurs. It occurs in order to make room for a new carbocation that is a lot more stable, for the negative Cl to come and attack. And I forgot some electron pairs here. That's fine. Okay? So now we can explain the methyl shift. And the methyl shift has the same exact concept. Okay? Suppose I have this structure. This structure in particular is called 3,3-dimethyl 1-butene. Right? And we're going to do the same reaction with HCl. Same reaction with HCl. So we know how this story goes already. When you add a hydrogen halide to an alkene, two things are going to happen. You're going to go through the formation of a carbocation intermediate, and it's going to obey Markovnikov's rule. Okay? So, what happens? Electron-rich nucleophilic center here will attack to this hydrogen, which is very electrophilic, because this bond is extremely polarized. Okay? So, again, we'll draw curved electron arrows. This will attack that. And then as a result, these electrons will come and deposit themselves onto the chlorine. Okay? So we were to draw this intermediate. And again, we must remind ourselves of Markovnikov's rule. Markovnikov's rule states that the hydrogen from the hydrogen halide, in this case, that's being added to this alkene is going to attach to the carbon with the most hydrogens attached to it. So which one of these carbons would that hydrogen attach to? Maybe this one. This carbon has 2 hydrogens, this one has 1. So that would be where this hydrogen would attach. I'll put it in red. So now we have a carbocation intermediate here, right? So the hydrogen came and attached to this carbon because it is the carbon with the most hydrogens in the one, right? According to Markovnikov's rule, in a very simple way. Okay, so there it is. And now this becomes our carbocation intermediate. Remember, this is the carbocation intermediate. Okay, but again, if we look at this carbocation and we say to ourselves, is this really where the Cl should attack? Is this stable enough? Or could it get more stable? Yes, it could get more stable. How? Well, we don't have a hydride shift in this one, but we have something called a methyl shift. So really what the methyl shift is going to do is that it's going to shift a methyl group. In this particular case, it'll be this methyl group right here, and its electrons onto this carbon, creating a carbocation here. And when that happens, that carbocation is now tertiary in comparison to this carbocation, which is only secondary. So we can draw some arrows showing a nice little equilibrium, you know. This intermediate form will always be favored more on this side than it will be on this side. So that's why I draw the arrows like this, right? And I'll abbreviate methyl with the word ME. And I'll put methyl shift. Okay? This is a nice little exercise for you to practice where these methyl groups will shift and where these hydrides will shift. Okay? So if I draw this, well, let's draw our electron arrow first. Okay? So this entire methyl group will shift and attack that positive carbocation with its electrons and everything. Okay? And this carbon would now become the carbocation. It would be a tertiary carbocation. So, drawing the structure, we'll get. And I'm running out of room here, but I'll try my best to. Be So we have our original hydrogen that was added, right? And then the methyl shift. That methyl group came over and came onto this carbon in the middle, right? So now the carbocation lies on the outside carbon. Now this carbocation is tertiary because it's attached to 1, 2, 3 carbons. Okay? So now we have a nice little stable carbocation for our Cl to attach onto. So the Cl will attack, the negative attacks the positive. So our desired product will end up being a very stable haloalkane. Okay? And that's pretty much it for methyl and hydride shifts. And if any of you want any more help or want me to do any more examples, please contact me at my email in the information box, and I'll be more than willing to help.